Welcome to Control System classes. The topic for today's discussion is Introduction to Controllers and in particular about P controller. What is a controller? A controller is a unit that is added in the feed-forward path of the basic elements of control system. A controller will produce the actuating signal, or it is also called as a control signal. The input for the controller is error signal. The error signal is nothing but the difference between the decide set point, which is nothing but the input, and the feedback signal, where the feedback signal represents the present output and the input is nothing but the decide set point. In order to achieve the desired output, the three types of controllers are possible. The controllers are named as proportional controller, integral controller, and derivative controller. In this class, let us discuss about a proportional controller. Here, the proportional controller from the name itself, we can able to understand it. The output control signal or actuating signal will be in proportion to the error signal. So mathematically in time domain, we can able to write u of t, the control signal, as proportional to the error signal e of t. To remove this proportionality symbol, let us add the constant kp, where kp is called as proportionality constant, or else we can also call this kp as the gain of the system. By taking Laplace transform of the given function, we can write u of s is equal to kp into e of s. Transfer function is nothing but Laplace transform of output by input with initial condition t is equal to 0. So when you write the equation output u of s divided by input e of s for the controller, the gain of the system is kp. It means the kp proportionality constant is nothing but the gain of proportional controller. It means we can also observe a point here. The proportional controller amplifies the error signal. It amplifies the error signal kp times. It means the speed of tracking is increased with the help of proportional controller. Let us discuss about a proportional controller with respect to the basic first order transfer function. Let us take g of s is equal to k dc divided by s tau plus 1, where tau represents time constant of first order system, k into dc represents the dc gain. It means when you substitute s as 0, the dc gain k into dc will be available, which is nothing but my final value, what we had discussed in the earlier videos. Let us take my open loop transfer function g of s as 1 divided by st plus 1. This is my basic first order system over which this is a transfer function what I am taking for the to analyze the system. So g of s is 1 divided by st plus 1. And also the gain of the system is kp. So I have added kp. What is my feed forward path? The feed forward path transfer function is kp multiplied by st plus 1, as these two blocks are in the cascade connection. And also the next step is I'm going to write C of s by R of s. So C of s by R of s, it is a negative feedback system. So the form is G of s divided by 1 plus G of s H of s, which gives Kp divided by St plus 1 plus Kp. Now to this function, divide numerator and denominator by 1 plus Kp. When you divide numerator and denominator by 1 plus Kp, and I'm rearranging the terms, and I got the expression like this. Now you compare equations 3 with equation 2. It means initial gain is 1. Now the gain is Kp divided by 1 plus Kp. So initial gain is 1. Now the gain is modified. And also let us compare the time constant t. The time constant t is initially for the given open loop system. It is simply t. Now the gain of the system, now the time constant of the system is t divided by 1 plus Kp. It means initial time constant is t. Now the time constant is reduced to t divided by 1 plus Kp. How it is said it is reduced? As when Kp value is increased, the denominator will be large and also the overall value will become a lesser value. So the time constant of the system is reduced. It means the time constant is less means it will reduce the rise time, peak time and settling time. But with reduced time constants, it may increase the overshoot. That is the opposite consequence of the reduced time constant. Let us find the steady state error with the introduction of P controller. The steady state error formula in S domain is limit S tends to 0 S into E of S. E of S is given by R of S divided by 1 plus G of S. G of S we have taken from the previous slide, that is assumed value what we had taken, it is substituted here and it is modified, but we got the steady state error ESS is 1 divided by 1 plus Kp. When Kp is 0, it introduces a constant value of 1. When Kp is infinite, the error steady state error becomes 0. But Kp is infinite is not possible. So when Kp is increased to a large value, it will destabilize the higher order plant. It will destabilize the higher order plant system. And hence, Kp of moderate value is only accepted. It means we can conclude it the steady state error will be always constant when we introduce a proportional controller to the original plant. Now let us compare all the concepts what we had discussed within a tabular form representation. So this is the first transfer function without my controller. Now I'm going to add a Kp controller of gain value 10. So my transfer function has changed to 10 divided by s plus 11. Similarly, this is for second order system without controller I have assumed. Now with controller I have assumed the value of controller that is of value 10. It is modified. The equation has been modified with the function with negative feedback, that is g of s divided by 1 plus g of s h of s form. Now substitute s is 0 and calculate the DC gain or steady state value for all the cases. So the DC gain is 1 here without controller. With controller, the DC gain is reduced to 0.909. It means now I'm having a steady state error. My final value required is 1, but the PI controller modification has decreased my final value, and hence we have a steady state error. And I have simulated these four transfer functions with MATLAB and using some command step info, using the command step info in MATLAB program, I got these parameters of time domain specifications. What are all time domain specifications? Rise time, peak time, settling time, overshoot, and so on. So let us correlate the first case, rise time without controller and with controller for first order system. So my rise time is initially 2.19. Now my rise time is 0.19 seconds. You compare with for second order system, my initial rise time is 0.9887 seconds. For the second case, my rise time has reduced to 0.2416 seconds. It means the introduction of P controller reduces my rise time, and also when you correlate the settling time, we can also see here my settling time got reduced, and also for first order system there is no overshoot introduced by the P controller. For my second order system, initial overshoot is 30%. Then with the introduction of controller, the overshoot has increased to 71%. It means the rise time is reduced. It means the speed of response has increased. In the opposite side, it increases the overshoot. And also, my peak time is also reduced. It means it reduces the time requirement of the system to reach the final value. But in the consequences, it introduces a steady state error, and also it increases the overshoot. Let us verify with the MATLAB. Let us see the MATLAB program for the how I had got this output. So here CLC clear all, close all, they are the basic commands to clear the command window and also the workspace. Close all is to close the figure window what you had run to close the figure window that is open during the previous execution of the MATLAB. Now without MATLAB, without controller, I'm interested to write the function in S domain. So I had written S is equal to transfer function of S. Then my P represents without controller, the function P represents with controller. So P is equal to my second order system. I'm interested to calculate the DC gain. So DC gain of P, it makes this S value to become 0 and will calculate the DC gain. I'm interested to plot 4 plots. So I had used the command subplot of. So subplot of rows, columns, position. So 4 plot I'm going to do. So 2 rows, 2 columns, first position. My x-axis scale, I have fixed 0 to 20 with an increment of 0.01. When the increment value is very less, the graph will be like a digital plot. When the increment is a very finite value, we'll get an analog plot, a pure analog plot. And I have declared my time. I have also used a command S1 as a variable where I am storing this information. Step info of P. It means this command only helps us to calculate the time domain parameters, and this command will print the time domain parameters in command window itself. Usually, by right-clicking the output window, figure window, we will see the time domain parameters. If you want to print the time domain parameters in the command window itself, you can use the command step info of the corresponding transfer function. So the first cases are without controller. Now I'm going to introduce a controller for the system of gain value 10. Now the commands you need, this is a fixed command, default command in MATLAB. C is a controller, C PID of KP. It means the function is PID of KP, KI, KD. So KP alone I am going to use. So KP, the remaining values the MATLAB will take it as 0. So C is equal to PID of KP. Now I'm going to introduce this controller. Now I'm going to introduce this controller of value 10 in series with P. So C into P, both are in cascade form. So C into P. So C into P, what is my feedback element here? My feedback element is unity feedback system. So C into P, my feedback value is 1. Feedback of this. So it means the MATLAB will calculate the transfer function of the given block diagram representation, right? So that function I have named it as T. Similarly, I have introduced the command step info of T. For first order system, I have taken the transfer function. So here I have named it as P1. The gain remains the same. The controller I have named it as P1, then T1. So 4 plots I'm going to plot in order to look about the response of the system with the introduction of controller. So let us see the output. So I have used the command 2 rows, 2 columns. So I got 2 rows and I got 2 columns here. So without controller, we can able to see from the figure window, my rise time is large here. But here with P controller for second order system, my rise time got reduced, but it has introduced my overshoot. Similarly, without controller for first order system also, here the rise time is large, here the rise time is less. And also you can able to observe here it introduces a minute steady state error in both the case, right? So let us summarize about the peak controller. The peak controller will amplify the error signal by E of S. The peak controller will amplify the error signal by Kp, and hence the speed of response will fast. The speed of response will introduce the overshoot of the system. And also peak controller will introduce as a constant steady state error. Increasing the Kp value will decrease the steady state error, but increasing a Kp to a larger value will destabilize my system. So the peak controller can be used if you want to improve, if you want to reduce your time domain parameters, with an opposite drawback with the introduction of steady state error. Thank you.